Look down here at the bottom at exercise 2.19. Show that if x sub n is an injective sequence in the real numbers, then x sub n converges to every point in R with the finite complement topology on R. Okay, so we have sequences and injective sequences and convergence in our topological space. So let's understand what those terms mean. Definition 0.30. Given a set x, a sequence in x is a function f from the positive integers, also known as the natural numbers, to x. Okay. And all right, so the nth term in that notation would be f of n, but we usually write x sub n instead, because that's a more familiar notation. And we can express the sequence in either of these forms. Okay. Now, so a sequence is a special type of function whose domain is the natural numbers. Now for any function, f from x to y, we say it's one-to-one or injective, those are synonyms, if whenever two outputs are equal, that implies that the inputs were equal as well. Okay. In other words, an injective function is one that maps distinct pairs of elements to distinct pairs of elements. That would be the contrapositor, right? If w is not equal to x, then f of w is not equal to f of x. Okay, and then convergence. In a topological space X, a sequence converges to a point X if for every neighborhood U of X, there's a positive integer capital N such that x sub n is in the neighborhood U for all n greater than or equal to capital N. Okay. So the idea here is that you might have heard of epsilon challenges in calculus or real analysis. Well, here you're going to be given a U challenge, right? Given any however tiny neighborhood U of X, and you can always find some place in the sequence, the capital Nth term, such that that term and everyone after it is inside of this little neighborhood U. Okay. And we say that x is the limit of that sequence, and we write limit as n goes to infinity of x sub n equals x. Now, all right, as we noted in this exercise, we're supposed to assume we have an injective sequence, and what would that mean? Well, okay, an injective sequence, and we want to show that it converges to every point in R in this topology, which is kind of bizarre, but we'll see how it works out. So what's an injective sequence? Well, it means that, so I want to take what's up here but write it in sort of this nicer sequence notation. Okay, so it would mean that x sub n equal to x sub m implies that n equals m, right? Or maybe it's nicer to write the contrapositive, say that if n is not equal to m, then that implies that x sub n is not equal to x sub m. Okay, so basically, no two terms of this sequence are equal to one another. Okay, that's going to be important. So now, I want to prove that every point in the real numbers is a limit of this sequence. Okay, so how about we let x be any real number. Okay. And now, from the definition of convergence here, we're supposed to take any neighborhood U of x, okay, and let U be a neighborhood of the point x. And, well, what do we know about open sets in this topology? This is the finite complement topology, which we've dealt with recently. And so, since U is open, we can say then U is equal to the complement of some finite set, right? Maybe we can name its elements y1 through, how about yr, okay? Just to have something a little more concrete to stare at. All right, well, maybe we can draw a little picture of what's going on here. So this set U is almost the entire set of real numbers, right? It's just missing finitely many points. y1, y2. I suppose I can assume I've written these down in order on the number line. Okay, and so on, and eventually y sub r. Okay, so that's what's missing from u. U itself is everything else in here, in between. Okay, so what we have is a sequence of real numbers which never repeats. And we want to show that eventually it has to stay in the set U. Okay? The idea is, well, it could be outside of the set U for a while, right? The terms in your sequence could be chosen from among these y's. But eventually you're going to run out of y's, okay? Or maybe you won't use some of them in the end. Okay? Eventually you're going to end up in the set U. So let's see if we can write down a proof of this. I need to, given this sort of U challenge, I need to give a capital N response, right? So what's it going to be? Well, I'm going to let capital N be basically the last, the index of the last term of the sequence, which happens to be one of these y's. Okay, so it's going to be the maximum of the set of n in the positive integers, such that that nth term is one of these y's. And, well, actually, that doesn't quite work because I need x sub capital N itself to be in U, all right? So I need to add 1 here just to get past that last potential problem. Okay. So if I have that, well then, whenever n is greater than or equal to, whoops, that's not the right symbol. Whenever n is greater than or equal to capital N, I need to show that x sub little n is in U. Okay. And, well, if n is bigger than, greater than or equal to n, then it's greater than the maximum of all of these indices such that x sub n is in the set of y's, right? So in particular, x sub n is not one of these y's. Okay. And that's just what we need, because that means that well, if it's not one of these y's, then it's in U, right? So we're done. Hence, this sequence x sub n converges this to this point x. Okay, but x was an arbitrary real number, so we are done.